This is the video presentation for multi-step recurrent Q-learning for robotic Velcro peeling. My name is Jiachen Yuan from University of Minnesota. In this video, we're going to talk about why we choose to study Velcro, what are the challenges, our problem formulation, our approach and baselines, as well as our results. To begin with, why do we choose to study Velcro? First, it is widely used in our daily life. We have it on shoes, clothes, cable ties, and etc. For human, because of our rich tactile sensing capabilities and the dexterity of our hands, we can open these deformable Velcros on various geometries, even with our eyes closed. So we want to know, is it possible for robots as well? Specifically, we want to design a controller so that the robot can successfully open the Velcro strips using only tactile feedback as input. To accomplish this study, we built experiment setup both on the real robot system and in simulation. On the left, we have a Kinova manipulator with a customized end effector, which has a tri-axis load cell to measure the force. On the right is our simulation environment in Mujoko. We model the Velcro strip with 2 layers of grid connected by breakable tendons. For simplicity, we only simulate gripper instead of a full manipulator. Now let's talk about why it is difficult for robots to peel the Velcro using tactile feedback. The first challenge we find is called tactile aliasing effect, which is an ambiguity between the tactile feedback and the end effector pose with respect to the Velcro. If you only look at the force at a single time step, many different poses can yield the same force measurement. Therefore, it could be challenging to infer the current configuration only from the current tactile observation. Another challenge we found, which we call the tactile void space, and we did an experiment to show its concept. For this experiment, we measure the force feedback while moving the manipulator along predefined trajectories. We parameterize the trajectories by theta, the angle between the peeling direction and the x-axis. Each straight line shows one peeling trajectory and the force magnitude along this trajectory. The lighter the color is, the smaller the force is. In figure B, C, and D, we vary the percentage of the Velcro that has already been peeled. We can see that after more Velcro getting peeled, the space with no meaningful tactile feedback gets larger and larger. Lastly, Velcro are often applied on non-flat surfaces, and unlike rigid bodies, the state of the Velcro cannot be modeled by only 6 degrees of freedom, making it challenging to precisely model the physics properties, such as contact dynamics. In simulation, we use this grid structure to capture the deformable property of the Velcro. We also introduce geometric uncertainties to the Velcro, as shown in the figures. We vary the translation of the Velcro origin in XY directions and rotation in all 3 axes. The Velcro strip is also applied not only on straight surfaces, but also on cylindrical surfaces with various radius. Next, I'm going to talk about how we formulate this problem. We discretize the Velcro into m pieces, and for each piece, we have a binary value on whether it is peeled or attached. Given this model, and the tactile and proprioceptive observation from the agent, our goal is to find an optimal strategy to control the end effector so that it can completely peel the Velcro. In this case, changing the Velcro states from all zeros to all ones. We then formulate it as in POM-DP. Here, the observation and state are given from the problem. The action is a fixed-sized movement of the end effector along XYZ directions. We use the number of peeled nodes at each time as a reward signal. Now let's go through some baselines and then talk about our approach. Before jumping into the POM-DP setup, we asked ourselves a question. What happens if we can actually observe the full state of the environment? Meaning we know the Velcro configurations and the end effector pose at every time step. In this case, the problem becomes an MDP, and we show that a simple strategy is sufficient to solve this problem. If we model the peeling boundary of the Velcro by two vectors, where V1 points the direction inward frame for the attached part, and V2 points the direction of the peeled part. Using the strategy by pulling V2 towards V1, we can actually achieve 100% success rate. Of course, things will not be that perfect in real-world scenarios. We couldn't attach sensors on every Velcro strips we have, and we don't always get a clean side view like the model we used. But what if we can use visual input and a network to predict these two representative vectors? We show that it is doable in some cases, but this method suffers from occlusion if the geometry gets more complicated. We call this approach vision greedy. Following this idea, we also studied whether it is possible to infer such information from tactile feedback as well. We used the recurrent network to process the tactile input and predict the peeling boundary vector V1 and V2. We call this method tactile greedy. Now, let's go back to the partial observability scenario with tactile observations as input. One existing method to solve a POM-DP is called DRQN, Deep Recurrent Queue Network. It takes one step of observation at each time step and maintains a latent representation using a recurrent network. Ideally, this latent vector should efficiently represent the history, and together with the current observation, it should be able to infer the state of the system, which should be enough to solve this problem. However, we found that the performance gap between the DRQN and fully observable case is more than 50%. The reason could come from two aspects. First, the tactile void space grows larger as more Velcro gets peeled, so the agent needs to travel longer and longer distance to get meaningful tactile feedback. Secondly, the DRQN makes decision at every time step, even if the tactile feedback is meaningless. So, in our approach, we used a longer observation sequence as input. When the tactile feedback is weak, the agent will not make decision on the actions, but stick to the current action. Once there is a strong feedback, the agent will make a new decision based on the observation sequence. Also, since the input sequence length is not fixed, we use a LSTM layer to process the input so that the decision module gets a fixed length vector z. The decision part is still Q-value prediction, which is made based on the hidden layer vector h from the last step and the current observation vector z. As a result, the time dependency of the memory becomes longer. The decision frequency slows down as well. That's why we call our approach multi-step recurrent queue learning. So how good is our approach? We evaluated our approach in both simulation and the real-world environment. In simulation, we made 3 test cases, from the easiest one on flat surfaces with only translation and 1 rotation along vertical axis, to the second one with extra tilt along x and y axis, all the way to the most difficult one, which includes cylindrical surfaces as well. On the real robot, we only tested on flat surfaces, and we fixed the Velcro base on the table, rotate the end effector frame to introduce the geometrical uncertainties. The quantitative results shows how many percentage of the Velcro each strategy can peel within the time limit. Basically, the longer the lighter region is, the better this strategy performs in these test cases. In each case, the leftmost one is the full observability strategy. Next to it is the open loop strategy, which randomly picks a direction and pulls towards it. The reactive strategy observes tactile feedback, but it uses only multi-layer perceptron to predict the action, so it doesn't have memory. We can see in the easiest test case, the vision greedy performs really well because there is no occlusion, but the performance drops very quickly when geometry gets more complicated. As a comparison, the tactile greedy is much worse than vision greedy, which tells us it is more difficult to infer the peeling boundary using tactile input than using visual input. Our approach, as shown in the last bar in each test case, performs most robustly against geometric uncertainties. To sum it up, we introduce Velcro peeling as a representative application to learn non-rigid robotic object manipulation. We proposed multi-step DRQ and network models. We compared with multiple baselines, and we evaluated both in simulation and in real world. Our code is available online. Thank you.